Welcome to The Explainer. Today, we're tackling a question that, every single data scientist has to face at some point.
All right, so picture this. You've just spent, hours, maybe even days building a predictive model. It looks awesome on paper. But how do you actually know if it's any good? I mean, really, will it work out there in the wild? That's the huge challenge we're going to break down today, how to get a truly honest read on our predictions. Think about it like this. It's kind of like a student who crams for a test by just memorizing the answer key. Sure, they'll ace that specific test. But the real measure of what they've learned, right? That comes when they face a brand new exam with questions they've never, ever seen before. And it's the exact same thing with our models. Because at the end of the day, performance on unseen data, well, that's the only thing that really, truly matters.
So, what's our goal here? Our mission, if you will, is to find that one honest-to-goodness score that tells us exactly how our model is going to perform on fresh, new, independent data it has never laid eyes on. The single biggest trap we can fall into is using the exact same data to both train and test our model. Now, why is that so bad? Well, it's because the model has already peeked at the answers. It's almost guaranteed to look way better than it actually is, and that gives us this really dangerous, overly optimistic feeling of confidence.
And this brings us to really a fundamental concept in all of machine learning, and frankly, the main villain of our story today. It's this massive difference between the error a model makes on its training data versus the error it's going to make in the real world. And that gap, that villain, has a name: overfitting.
Okay, to really wrap our heads around this, let's just visualize a simple chart. So along the bottom, the horizontal axis, you've got model complexity. Think of it as going from super simple on the left to incredibly complex on the right. And then on the vertical axis, you've got prediction error, where of course lower is better. All right, now let's trace that first line, the training error. What happens? As we make our model more and more complex, it just gets better and better and better at fitting the data it was trained on. Just look at that error line. It just keeps dropping, pretty much heading towards zero. On paper, this looks amazing, like we've built a genius model.
But, and this is the big but, here's the twist. The error on new, unseen data, it tells a totally different story. It starts out high, then it goes down as the model starts to learn the real underlying patterns in the data. It hits this perfect little minimum point. That's our sweet spot. And then, as the model gets too complex, the error starts to climb right back up again. It creates this really distinct U-shape.
And that right side of the U-curve? The part where the model is an absolute genius on its training data, but a total failure on new data? That is the textbook definition of overfitting. What's happened is the model has stopped learning the general signal and has started just memorizing the random noise and quirks of the specific training set it saw.
Okay, so the big question is, how do we find that sweet spot and totally avoid this overfitting trap? Well, the most intuitive first step, the thing most people think of first, is what's called the validation set method. And it's simple. We just split our data.
So the process seems pretty straightforward, right? You just take all the data you have, you randomly chop it in half, you use one piece to build the model and the other piece to test it. Easy peasy, or is it?
Yeah, well, not quite. This simple split actually has two pretty major flaws. First off, your final score can swing wildly, just based on pure luck. Which individual data points happen to land in the training set versus the validation set. And second, because you're only training on a fraction of your data, the model itself isn't as powerful as it could be. And that usually means you get a test score that's actually worse, more pessimistic than the truth.
So that simple split is out. Let's move on to a much, much more robust and frankly clever solution that solves both of these problems. Let's talk about k-fold cross-validation. Okay, so instead of that one single risky split, k-fold cross-validation is way smarter. What it does is it divides all your data into several equal sections, we call them folds. Then it trains and tests your model multiple times, and each time it rotates which fold is the designated test set. So by the time it's done, every single data point has had a turn being in both the training set and the test set. Then you just average all the scores together and boom, you get a much more stable, much more reliable estimate of performance.
And here's the great part. You don't really have to guess how many folds to use. Decades of research and practice have kind of shown that using 5 or 10 folds, so a K of 5 or 10, that usually gives you a really reliable estimate of your model's true performance without being, crazy expensive to compute. It's really the go-to standard in the field.
All right, this next point is absolutely crucial. This brings us to probably the single most common and dangerous mistake people make: data leakage. Here's the rule. Any step that learns from the data, and I mean anything, like selecting your best features, it has to happen inside each of those cross-validation loops. If you do it beforehand using all your data, then your test set isn't truly unseen anymore. Your model has gotten a sneak peek, and your score, it's going to be a lie. The entire pipeline, from start to finish, has to be validated.
Okay, so cross-validation is fantastic. It's our hero for estimating the final prediction error of our model. But what if you have a totally different kind of question? What if you want to know how stable or how uncertain your model's internal guts are, its parameters? For that, we're going to need a different tool.
And that tool is called the Bootstrap, which, by the way, has an amazing name. It comes from that old tall tale about Baron Munchausen pulling himself out of a swamp by his own bootstraps. And you know what? It's a pretty fitting name for a technique that essentially creates new data out of thin air. Or, to be more precise, out of the data it already has.
So here's the core idea behind it. We can't just go out and collect thousands of new, real datasets, right? That's impossible. So the Bootstrap simulates them. It creates a new dataset by randomly picking data points from your original set. But here's the twist. Every time it picks a point, it puts it back into the pile before picking the next one. This is called sampling with replacement.
So you can see here, right, in that first Bootstrap sample, the data point C got picked twice, but B didn't get picked at all. Then in the second sample, B shows up twice. So each new sample is the exact same size as the original, but it's a slightly different version of reality, a slightly different combination of the original points.
Okay, so why on earth would we do this? Well, it's because now we can run our analysis. We can fit our model or calculate whatever statistic we're interested in on each of these thousands of slightly different data sets. And by looking at how much our result jumps around from sample to sample, we get a direct measurement of its stability, of its uncertainty. We can actually calculate things like its standard error.
Okay, so let's be absolutely crystal clear about this. Cross-validation and the Bootstrap are both what we call resampling methods, but they answer totally different questions. Cross-validation is all about estimating your final prediction error, and its key feature is that there's zero overlap between the training and test sets. The Bootstrap, on the other hand, is for estimating uncertainty, and its key feature is sampling with replacement. You really have to think of them as two different, powerful tools for two very different jobs in your toolkit.
And in the end, look, knowing how to get an honest score for your model, that isn't the end of the journey, it's really just a beginning. It gives you a reliable benchmark, a true north, that lets you experiment and tune and really build something that you can genuinely trust to work. Because let's face it, you can't improve what you can't honestly measure. And that honest evaluation, it's the foundation of every single great model ever built.